Okay, so let's talk about phase changes as part of the Module 8, Heat Transfer and Phases of Matter. You probably are familiar with the three primary phases. We've got our solids. Solids have a definite shape and volume. Atoms and molecules are closely spaced, and the positions are pretty much fixed. And solids are incompressible. So if you apply a pressure to them, they're not going to change in volume for the most part. You know, if you have something like foam, obviously that's going to change, but solids in general have are incompressible. Liquids have a definite volume, right? You could have 100 milliliters of water, but if you pour that water in one container versus another, right, it's going to take the shape of that container. So no definite shape. And internally, the reason water is different than a solid is because the atoms or molecules are more widely spaced, right? There's a lower force of attraction between them. And liquids, for the most part, are nearly incompressible for most intents and purposes. Finally, we have gases. Gases really have no definite shape or volume, right? If you fill up a balloon with helium, it's basically whatever the shape of that balloon is, right? So you can have different shaped balloons. The helium just takes the shape of that container. The atoms and molecules are pretty widely spaced. It's really basically very random motion, very little structural bonding, if any at all, between molecules. And gases are compressible, right? You can take them and you can put them in a container and you can squeeze them and make them a smaller volume, and the pressure is going to increase, obviously. All right, here's a visual representation of the three phases, right? We got solid over here on the left. Nice rigid fixed shape, fixed volume, you can't squash it. Now you put liquid in the same container. It's not rigid, right? Notice it's no fixed shape, but there is a fixed volume, right? This area above it is not liquid. And then a gas, you put it in the same container. It's not rigid or fixed in shape, and the volume is just whatever the volume of the container that it's in. And this can be squashed. All right, so let's talk about phase change. What happens when you go from a solid to a liquid, or the same idea, liquid to a solid, right, backwards? I'm going to refer to this diagram on the side here. Let's go through the bullets. First, we have energy involved in a phase change goes into either breaking or forming bonds. And we call this the latent heat. And latent is a word that means hidden. Comes from I believe it's Latin. Latent heat is hidden heat. And that's a very appropriate name for latent heat. Because what happens? Well, for melting, for example, let's take melting. You've got ice over here, and it starts melting. These bonds between molecules break, right? So now you're left with sort of individual molecules floating around as a liquid. So that's what happens when you melt, right? You can also have the reverse happen. You can have freezing. So notice this diagram: melting absorbs energy, right? Freezing releases energy. So in this case, we're going now backwards. The liquid molecules are releasing energy, and they're getting slower and closer together until they bond again, and then they form a solid. And a key thing here is that freezing and melting take place at the same temperature, right? So for example, for water, it's 0 degrees C. There's no temperature change happening during a phase change. And this is one reason it's called latent heat, right? You keep putting, so for example, for melting, you keep putting energy in and you don't see a temperature rise. It's hidden heat. You can't see a change in temperature. But it does go into changing the phase of the substance. And for melting or freezing, right, we have what's called the latent heat of fusion. So fusion, you can think of, you're fusing these together, these molecules together. You're freezing the object. And one other thing for the conservation of energy, remember energy is neither created or destroyed, but whatever heat you absorb when you melt something is the same amount of heat that you release when you freeze it, right? So for example, you have you freeze some ice cubes, and you take a certain amount of heat out, right? When you put those ice cubes in a glass and they melt, they're pulling a certain amount of heat out of the liquid and cooling that liquid down. Okay, let's talk about now liquid to vapor or vapor to liquid. Comment about the jargon here. We typically refer to a vapor is whatever, if we have a pure substance as a liquid, when that pure substance evaporates, it's a vapor of that substance. A lot of times vapor is used, let's see, if it's a liquid at room temperature, it's typically called a vapor in the gas phase. All right, so what do we have? We have boiling, and boiling is over here, right? Evaporation or boiling. A liquid absorbs heat, bonds break even further, and you get this vapor. So look at these little molecules running around in the vapor phase. Condensation is when the gas releases heat, right, to some, either its environment or some surface, and then it slows down enough the bonds can form again and it forms a liquid. And again, just like freezing and melting, condensation and evaporation, or boiling and condensation, take place at the same temperature. And this is called the latent heat of vaporization. Again, conservation of energy tells us that whatever heat we absorb, the gas absorbs to evaporate, is the same amount of heat it's going to release when it condenses. All right, here's an example for water. This is a phase change during heating. So what do we have going on? Well, in the first section here, we start off as ice, right? Minus 20 degrees C. And then we start warming up the ice, warming the ice, warming the ice. And we discussed specific heat. So in this section here, the temperature change is governed by the specific heat of the ice, right? However much energy we're adding. So here we're adding a constant heat input. So calories per, or joules per kilogram degrees C, or calories per gram, whatever degrees C, whatever heat capacity you're using, that's what's governing this temperature change. As you add energy, the temperature raises as a function of the heat capacity. Then we start melting, and notice what happens in melting. We have a plateau. This is a constant temperature. This is your heat of fusion. You're putting in heat, right? It's a latent heat of fusion. Again, a latent heat is a hidden heat. You don't see a temperature rise, you just see a phase change. And then we get to this point here, and we have all liquid water. And then what happens? Well, now we have the heat capacity of water. So this warming, right, how much temperature it rises and what rate is governed by the specific heat of water. So again, we're putting in a certain amount of calories. Calories per gram degrees C determines the slope of this line. Then we reach the phase where we're at 100 degrees C and we start boiling the water. And this is your latent heat of vaporization. So boiling, we're putting this heat in, the water's changing phase, right? It's like the water in the pot on your stove. It's starting to boil. And then at some point we hit this spot here and we've got all water vapor. and that water vapor is just warming, right? So now when the water vapor is warming, now this is steam, right? This is the heat capacity of steam. So that's what governs this warming curve. So you could continue to heat up the steam or the vapor and increase the temperature that way. All right, so just a quick summary. Again, the phase changes solid to liquid. This is the melting point, right? It's absorbing energy. Liquid to solid, that's the freezing point. It's releasing energy, right? So let's think about this. The solid to liquid. In order to go from a solid to a liquid, the solid has to absorb energy. In order to go from a liquid to a solid, the liquid needs to release energy. Liquid to vapor or a gas, this is the boiling point, right? And to go from liquid to vapor, you need to be absorbing energy. And then vapor to liquid is the condensation point. And again, to go from vapor to liquid, you're releasing energy.